ECHO is a Bayesian approximation model for in silico drug screening in genomic medicines. Genomic medicines are complex systems in which many components drive efficacy. However, only a fraction of the design space can be experimentally assayed due to time and cost limitations. Existing datasets are conducted in settings that often translate poorly to real-world clinical and therapeutic contexts. Here, we saw a need for developing a tool that can enable the cost-effective optimization of genomic medicines while working with sparse datasets. ECHO is a Bayesian approximation model for this task. Here, we use a lab-in-the-loop modeling workflow where we iteratively assay a small panel of in-context data, generate context-aware predictions, then assay our predicted hits. We use a weighted ensemble of gradient-boosted decision trees, where each learner is weighted by its out-of-bag loss. Together, this enables us to predict our top screening hits, and importantly, also get a measure of epistemic, or model, uncertainty for each hit. Our model trains on 76 features, which include position-independent nucleotide composition, as well as nucleic acid binding energies. In our in silico benchmarks, we saw that our model was able to outperform state-of-the-art methods. On the left, we see an example of our model outperforming publicly available models in the context of diverse targets in T-cell and hematopoietic stem cell endogenous loci. On the right, we show the motivation for the selection of our model, comparing our model to classic approaches, both across Bayesian and deep learning methodologies, showing that in those cases, given the sparsity of our dataset, more complex models often overfit or more poorly performed in our context, motivating the choice of our lightweight learners. We saw that our model was able to demonstrate high data efficiency across diverse targets, where our model required less than 55 data points to train for new contexts. This is important because it allows us to reduce screening cost. Our model identified potent hits at 10% of the cost of a full screen. This also helped us reduce the turnaround time, accelerating the design, build, and test cycle, and reducing the time to lead candidates by up to 50%. In experimental in vitro validation, we saw that our model was able to increase hit potency across diverse therapeutic targets, with our model generating candidates with genomic editing efficiencies between 71 and 85%. It's important to note that in targets E and F, we did not see a statistically significant improvement in our model's predictions compared against our benchmarks. And we expect in these cases that the genomic medicines may have already reached their maximum editing performance even among the training set. In conclusion, we see that ECHO enables the cost-effective optimization of genomic medicines. We show that ECHO was able to increase potency, reduce cost, reduce turnaround time, and do so in a data-efficient manner, which allows agility in enabling rapid pivots between new cell types and new contexts.